Harvage criteria can be used to find the stability of the system. So we can find generally closed loop stability of the system if you know the open loop transfer function or if you know the characteristic equation of the system. We know how to form Routh's array, and from that we can look at what are the first column of the Routh array. So once you know the first column, then look at the sign. If there are no sign changes, which means system will be stable, provided that there is no row contains any 0 elements. There are other applications of RH criteria. So one such application is finding the range of gain k for system stability. You will be given a system with one tunable parameter, that is open loop gain k. Usually that gain k can be varied, and I want to know for particular system what should be the adjustable range so that my system will be within the stable only. Why do we adjust the gain? To get the desired performance of the system, right? So but we should not go beyond a certain value. So what will be the limiting value of k? What will be the maximum allowable gain k in your system? So that we can also find out using RH criteria. So let us look at some of the examples to understand how can you find the range of k values for system stability using RH criteria. The open loop transfer function of a control system is given by gh of s is equal to k divided by s plus 2 into s plus 4 into s square plus 6s plus 25. Find the k value such that system will have a sustained oscillations, and also find the frequency of oscillations. So this is the problem. So here it is given open loop transfer function. If open loop transfer function is given, we can find out the characteristic equation, because to form Routh's array we need characteristic equation. Now, so in this case we don't want k range values, we want what is the exact k value such that system will give you sustained oscillations. So when you will get the sustained oscillations, if the system is marginally stable. So when system will be marginally stable in Routh's array, if at all any row contains all 0 elements. So if any row contains all 0 elements, which means there is a possibility of poles that are on imaginary axis, then you will get the marginally stable condition, then we will have sustained oscillations. So we need to find what will be the k value to get such situation, and what will be the frequency of oscillations, how those frequency at what frequency oscillations will be. Okay. Now, so we will take the open loop transfer function. We know that gh of s is k divided by s plus 2 into s plus 4 into s square plus 6s plus 25. Characteristic equation is 1 plus gh is equal to 0. Then if we substitute here, we will get here it as, when you multiply all the terms, then we have s power 4 plus 12s cube plus 69s square plus 198s plus 200 plus k is equal to 0. So when you multiply 1 plus gh is equal to 0, when you simplify, you will be getting this characteristic equation. And in this characteristic equation, I have one variable parameter k. So as I said, we need to find k such that system will give you a sustained oscillations. The response of system will oscillates continuously. So we take the Routh array, the highest degree here it is 4. So s power 4, s cube, s square, s power 1, s power 0. We need to fill all these rows, and the first two rows will fill with the coefficients of the characteristic equation. Now what will be the first one? From the characteristic equation is very clear, we can fill it as 1, 12, 69, 198 and 200 plus k. So these are the two rows we can fill. Then coming to the next row, s square row. So s square row, how can you write here? So we can write directly 69 minus, we have 198 divided by 12, because 198 into 1 divided by 12, or else we can directly multiply the 12 into 69 minus 198 into 1 divided by 12. So which gives us 52.5. The value of this is 52.5. So what will be the next element? Next element is very clear, the above is 0 and above we have 200 plus k, that will be carry forward to here. That is 200 plus k is the next element of, second element of my s square row. Then how to calculate s power 1 row? The procedure is same. So we will take here 52 and this element is we have 198. So we have 200 plus k and here I have 12. Then these two multiply, these two minus these two divided by this. So which gives us 52.5 into 198 minus 200 plus k into 12 divided by 52.5, or else directly we can write it as 198 minus 200 plus k into 12 divided by 52.5. Now, so what will be the last element? Last element calculation not needed, already I have 200 plus k, so that can be taken here, it is 200 plus k. So this is the complete routes array. In this routes array we have all first column elements with the variable parameter k. Now if you closely observe the first column elements, I have 1, then 12, then 52.5, then I have here 198 minus 200 plus k into 12 by 52.5, and this will be 200 plus k. Now first column elements are ready. Then what we will do next? So in the problem we said we need to find the k value such that system response will oscillate continuously, system will have sustained oscillations. Therefore I need to get the marginally stable condition. So marginally stable condition in the sense the one row should have all 0 elements. Let us try to make the last row with all 0 elements. So when I take this, then 200 plus k is equal to 0. So when I say 200 plus k equal to 0, k is going to be minus 200, but k cannot be negative. K should be always positive and it should be a real value. So if at all we get a complex value also, that is not acceptable. So k must be real, k must be positive. So this condition is not valid. That we take the second condition. Now 198 minus 200 plus k into 12 divided by 52.5 is equal to 0. So if you solve simply, then you will be getting a k value as 666.25, 666.25. So this is the value we are getting, which means when you choose the k value 666.25, then one of my row, that is s power 1 row value will be 0 and other value also zeros. So that means this row completely 0 elements, and since you are getting one row with all 0 elements, then you will be getting a marginally stable condition. Once you get the marginally stable condition, system will have continuous oscillations. Now the first part of the problem is completed. That means find the k value such that system will give you continuous oscillations, sustained oscillations. Then when I choose the k value 666.25, you will be getting that condition. But what will be the frequency of oscillations? So the frequency of oscillations is nothing but the location of the pole. Then how to find the location of the poles on imaginary axis? Solve auxiliary equation. Now we have already k value 666.25, then I can substitute that in the auxiliary equation. Then what will be the auxiliary equation? Auxiliary equation is formed by the coefficients of the row which is just above the row which contains all 0 elements. So now s power 1 row with all 0 elements, then take quotient of s square row. So what is s square row elements? We have 52.5 and also we have 200 plus k. So k we need to take that value 666.25. When you take here 52.5 s square, I am not writing s term because we need to miss the one term. 52.5 s square plus 200 plus 666.25 is equal to 0. Then you try to find the s value, then the s value is going to be plus or minus j 4.06. So what is this s is equal plus or minus j 4.06? There are two poles on imaginary axis on s plane. So one is at plus j 4.06 and the minus j 4.06, two poles on imaginary axis. Now, so I have one pair of poles, therefore there is no problem at all. So system will be marginally stable only. Now we know that the s is equal to j omega. We can substitute s place, we can substitute j omega. Then j omega is equal to plus or minus j 4.06, you can cancel j, then omega value is your 4.06. You take the positive value because frequency always positive, we should take the positive value. Omega is 4.06 radian per second. So this is the frequency of your sustained oscillations. So we will have continuous oscillations, and these continuous oscillation will have 4.06 radian per second.